per volts. Microampere per volts. So del ID by del VGS, keeping VDS equal to 0, is your transconductance. Okay, or in other words, because the changes in the ID and VGS are equivalent to AC current and voltage, the equation can be written as GM is ID by VGS if VDS is equal to 0. Is it okay? So the unit of GM is mho or Siemens. Typical value of GM is 2000 milliampere per volt. Is it okay, friends? Now your equation you have ID equal to IDS 1 minus VGS by VP whole square. You have to differentiate it with respect to, I can call it DID by dVGS also. With respect to VGS, if you will differentiate it, you will get your GM. Okay. And what is the RD? RD is the drain resistance only. Drain resistance means RD is, what is the drain voltage? VDS. What is the drain current? ID. So, keeping VGS is equal to 0. Please remember this. RD is the drain resistance. Definitely it will be VDS by ID but at VGS equal to 0. Is it okay to you? Okay. Now FET is an amplifier. This is the FET equivalent circuit. We have seen the equivalent circuit of the BJT earlier. Now similar to bipolar junction transistor, JFET can also be used as an amplifier, and the AC equivalent circuit of JFET is given below over here. See, this is the input resistance I'm choosing. Gate terminal, source terminal and drain terminal. Okay. From gate to source, the voltage is VGS. Okay, fine. So the resistance between gate and source is very high, RGS. Or you can take it open circuit also, but I'm taking it RGS. And what about this current? This is ID. Is it correct? And we have seen just now GM equal to ID by VGS. So ID will be GM into VGS. So this is VGS actually. Is it okay? And this is the output resistance RDS. So the resistance between the gate and the source is RGS taken over here is very high. The drain of JFET acts like a current source with a value of GM VGS. This is the drain. In the drain the current is GM VGS. Is it okay to you? This is equivalent circuit of the JFET, and JFET we can use as an amplifier also. In which region we'll use it in amplification? In saturation region. In saturation region only. Okay. In the saturation region only we'll get the stable Q point. Okay. Wait a minute. Now let's come to the next one. See, from the AC equivalent model, ID is GM VGS plus VDS by RD. When ID equal to 0, this is the relationship between VGS, VDS and ID by AC model of this circuit, whatever we have seen. Okay. So ID equal to, when ID equal to 0, you will put over here, your equation will be GM VGS plus VDS by RD equal to 0. So finally VDS by VGS equal to minus GM by RD. Is it okay? So the amplification factor mu for FET is defined as VDS by VGS at ID equal to 0. So mu is the amplification factor in the FET. Mu is the amplification factor and given by VDS divided by VGS. Is it okay? And this is mu is nothing but GMRD. GMRD. If you write the GM is ID divided by VGS. If we talk about RD, so it will be VDS divided by ID. ID will get cancelled. This is mu. So mu is nothing but VDS by VGS, VDS by VGS. But in terms of you want to write in terms of transconductance, then amplification factor mu is nothing but GMRD. Is it okay to you? Now when VGS equal to 0, GM has its maximum value. Conductance has its maximum value because at VGS equal to 0 only we have seen Imax. Imax will be possible when conductance will be maximum. So the maximum value is designated at GMO. Again consider the equation. See, this is the equation. ID equal to IDSS 1 minus VGS by VP whole square. If you want to get a GM, and the definition of GM was del ID divided by del VGS. Is it okay? So we differentiated with respect to VGS. When you will differentiate it, let me differentiate over here. So GM will be IDSS constant. This 2 will come out 1 minus VGS by VP into minus 1 by VP. Is it okay? Finally, you have 2 IDSS divided by VP 1 minus VGS by VP. Now condition is this GM will be max at VGS equal to 0. Put VGS equal to 0 over here and give its name GMO now. Minus 2 IDSS divided by VP. So this is your GMO. Is it okay? So as VGS increases, GM decreases. This is the relationship. Now in this equation you can put minus 2 IDSS equal to GMO. So our equation will remain with, see, this term is GMO. So now new equation will be GM equal to GMO 1 minus VGS by VP, where this VP is nothing but your pinch off voltage. Is it okay to you? So pinch off voltage if you want. So pinch off voltage minus 2 IDSS divided by GMO is given. I hope it's clear to you. Okay. Now common source amplifier. Here also in FET also we'll see common source, common drain and something kind of amplifiers. See, I'll tell you what is the motive of this. See, where is the source? Here is the source. The source is connected with parallel capacitor. We have seen in the BJT also. There also your BJT was connected with, suppose emitter was there, emitter was connected with capacitor in parallel, it means it was common emitter. Here I connected this capacitor with parallel with RE source, so source is common here. Output we are taking at the drain terminal, input I am giving to gate terminal. So if you will observe this is the gate waveform. Gate waveform is appearing on the drain output. Okay, so this is the amplification. Whatever you are giving, the same thing you are getting in terms of waveform. Okay, it may be amplified or whatever, but it should not be distorted. Okay, wait a minute. Now, when a small AC signal is coupled into the gate, it produces variation in the gate source voltage. Definitely, this produces a sinusoidal drain current. Yes, this is the sinusoidal drain current over here, since an AC current flows through the drain resistor. Definitely, an amplified AC voltage is obtained at the output. An increase in the amplification will be by the factor of mu. We have seen mu is nothing but VDS divided by VGS. So your VGS will be multiplied with mu and you will get the output. Okay. Since an AC current flows through the drain resistor, an amplified AC voltage is obtained at the output. An increase in gate source voltage produces more drain current. Okay. Which means that the drain voltage is decreasing. Since the positive half cycle of the input voltage produces the negative half cycle of the output, See, if you are applying positive, in the positive half cycle, you are getting the negative. It means this is the inversion of your signal. So we get phase inversion in common source amplifier. So common source amplifier is similar to common emitter amplifier. In the common emitter amplifier, we have seen there is a 180-degree phase shift between input and output. Input and output we have seen there. Is it okay? So common emitter amplifier is similar to common source amplifier. Is it okay to you? If we'll talk about the circuit, we'll see in the problems only. Okay. Now this is the equivalent circuit. This is the equivalent circuit for this one. AC and DC equivalent circuit. We will apply the AC analysis, DC analysis, then we have to find this. Is it okay? Equivalent circuit, AC circuit is R1 and R2 input resistances are in parallel. VGS is there across, and here Vin we are applying. This is RGS. The current ID is nothing but minus GMVGS. Here is the RD, and here we are taking the output for this circuit. So like this. So now we will see only questions, numericals. Here we'll see symbol of FET. Okay. The symbol of FET is given like this is drain, this is source. It's like simply this. Okay. So this is for N channel. For the N channel, it will go inside N channel, and for P channel, the arrow will come outside. This is P channel. This is for P channel. This terminal is drain, source, and gate. Between gate and source, the voltage is VGS. VGS. Here, the voltage is VDS. Okay. And one more important thing is, while considering the problems, IG is always equal to 0. Is it okay? So this is the symbol of FET. Let's come to MOSFET now. See, we have seen the FET, the field effect transistor, divided in two categories. Number one is JFET, junction field effect transistor, and the second is MOSFET, metal oxide semiconductor FET. Okay, so we have seen FET's working and problems, right? After finishing MOSFET, we'll start the total problems related to MOSFET and FET. Okay, so this was the channel over here, there in FET, P-type gate, both sides. Here it was drain, it was source, the current ID was flowing there. Is it okay? So here we have channel N, and because of that we are having current ID, and that current ID we are controlling by the application of VGS in the FET. Now MOSFET is little different. How we made up this MOSFET? See, in this diagram shown over here, in the JFET, if we'll talk about, we are having three terminals. One is for drain, source, and gate. But here we have four terminals, one extra because of this body. Okay, so what is going on over here? See, source as it is, gate as it is, drain as it is. But the source with N plus and the drain with N plus is merged into P type of substrate. Okay, so this is like platform for source and drain, and in this all conduction will happen like this over here, and again the controlling element is gate. Okay, so in the MOSFET, actually we have seen the JFET, right? JFET was faster than BJT. See, BJT, and then FET, and more advanced version is MOSFET. Okay, so the advantages of MOSFET are more than FET and BJT. Okay, input resistance is high over here, here extra high. Output resistance is high over here, here also high. Thermal stability is good, here also good in MOSFET. And FET is bulky, but MOSFET is very simple to construct. This is like BJT, this is like FET, and this is like MOSFET. Now you can easily understand what is the MOSFET. The fabrication of MOSFET is very easy nowadays in ICs. Basically we are using the MOSFET. So friends, briefly I will tell you how it works. See, MOSFET is divided in two categories. MOSFET is divided into two categories. One is depletion MOSFET and second is enhancement MOSFET. Okay. In the depletion MOSFET, between source and drain, one depletion region will be already provided. See, one channel will be provided already. Here I'll be having many electrons. Okay, like this. This channel is predefined in the depletion, and this channel is called the depletion region. But in the enhancement mode, there will be no such channel provided. Okay, so in the depletion mode we have already provided channel, but in enhanced mode we have to develop this channel. Okay, so one by one I'll tell you the working in brief. Okay, so depletion, if I'll talk about, so in the depletion, see, the situation is like this is SiO2 layer. Okay, it's insulating the gate from substrate. Here N plus, here N plus. Okay, this is drain. Source. Over here I'm providing gate. This is P substrate. Okay, and if we are talking about the depletion, already the channel is provided. Okay, wait a minute. This channel is provided already, depletion. So this is depletion MOSFET. How it works, we will connect battery over here between VDS like this. Is it okay? And VGS is like this, VGS. Okay, now what will happen? When we'll apply VDS, there will be current into the circuit. Is it okay? Because this region is already existing, depletion region, channel, you have the channel. So over here you will get the current, ID. So this ID I call the IDSS. This is the maximum current in depletion mode of MOSFET. Okay, and this is the condition when VGS equal to 0. When VGS is equal to 0, it's simply looking like a resistor. You are applying VDS, you are getting current, that IDS. But if you introduce VGS, there will be something. So VGS is in this way, minus, 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 all positive charges will accumulate over here, and they will create unnecessary obstacle in between the path of electrons over here. So current will decrease now. If you will apply some VGS in the circuit, the current start to decrease, this VDS. Okay, so by applying VGS, in this way you can control the current IDS. Okay, but the story is different in enhancement. In the enhancement mode, what is going on there? But a minute. This depletion layer is not there in the enhancement. No channel is provided with us. Okay, so what we will do is, we'll apply the VGS in this way, VGS. Now if VGS equal to 0, there will be no current, 0 current. Okay, This is the condition for enhancement. In the enhancement mode, when VGS equal to 0, there is no channel. So there will be no current in the circuit. If you want to flow the current or conduction, you need some channels over here. Okay, or some electrons over here, but you don't have the electrons. So in the enhancement, ID equal to 0 when VGS equal to 0. Okay, so we have to apply some VGS, and this VGS should be greater than threshold voltage of the system. Threshold voltage is the minimum voltage, after that conduction will start. Okay, so when you will apply the VGS over here like this, so here negative electrons will accumulate. The magnetic area of this P substrate will accumulate over here. Okay, they are going to accumulate here and creating the path or creating the channel. Now current will start to flow in the circuit, right? So once this VGS cross the VT, now if you are applying VDS, you are getting IDS, and it will increase as the VDS increase. Okay, and the saturation occur when VDS is equal to VGS minus VT. When VDS will be exactly equal to the VGS minus VT, then saturation will be there in the system. Means at the time ID will be IDSS. So in the depletion layer, depletion channel was already present in the system. So that's why at VGS equal to 0 we were getting maximum current. But as we applied the VGS, the current started to decrease there. But in enhancement mode, initially there was no current because VGS was 0, so channel was missing. We applied the VGS, positive VGS, channel started to build there in between two drain and source materials. Okay, N and N plus N plus. So in between them channel is formed, and then current is going to start now. This current at some point, means the voltage equal to VGS minus VT become constant, and the constant current given is IDSS, or in other words I can say the saturation of the current occurs at VDS equal to VGS minus VT. Is it clear to you? So we'll see now the characteristics. Okay, let me erase it. In the depletion mode, the current was already like, the situation was, the current was increasing in this way. After some time it was getting saturated. Is it okay? The situation is same, and the voltage is VP. The situation is like this. This is ID and VDS. Is it okay? And if we'll talk about ID and VGS, here only I'm drawing it. As you applied the VGS, ID decreased. Okay, initially ID was max, IDSS. But as you applied the VGSS, ID going to decrease, and at some point ID is become 0. This is related to depletion. But if we'll come to the enhancement, initially the current is 0. Then the current is going to increase. Is it okay? Let's take it VDS. Let's take it ID. So up to VT, there is no current, 0 current. But after VD, the sudden current is there. In the enhanced E only MOSFET I'm talking about. Is it okay? VT is, after VT, after threshold point, there is the current over here. And after some time it will be saturated. Like this. So this is depletion graph starting at 0, but this is not starting at 0 because we have threshold crossing. Okay, before threshold crossing the current will be definitely 0. Is it okay? So this is the brief introduction or brief working about the MOSFET and FET. Now I'll give you the current. For this, the current equation is ID equal to whatever we have seen in the FET, 1 minus VGS by VP whole square. Okay, but E only MOSFET, the current equation is given as, actually in this E only MOSFET, if we are having two regions, ohmic region and saturation region. Ohmic region means VDS should be greater than VT, but should be less than VGS minus VT. This VDS should be greater than VT, then only I'll get the current. But also at the same time, it will be less than VGS minus VT. Because at VGS minus VT, we are getting saturation. If VDS is greater than VGS minus VT, will behave saturation region. And before that, we are having triode region or ohmic region. Okay, so current is given, current formula is given. It's mu n COX by 2 omega by L VGS minus VT into VDS. I'm sorry, this 2 is not here. So COX is the MOSFET capacitance. Okay, oxide capacitance also I can call. This is with length VGS minus VT into VDS and minus VDS square by 2. This is the whole formula for E only MOSFET. Okay, so this is about the brief. Now I'll take the problems, then only you will understand. Okay, this is the gate problem and the question is given as, let me take circuit first, let me draw it. This is N channel, JFET is given, RS connected with 10 volt given. In this circuit I have ID and it's directly connected like this. Now the question is, the JFET in the circuit shown in the figure has an IDSS. IDSS is the max current. IDSS is given 10 milliampere and VP is also given. VP is minus 5 volt. The value of the resistance R is, they're asking for this. Find out the value of resistance R is for a drain current. For a drain current, ID is equal to 6.4 milliampere. And your options are given: 150 ohms, B 470, C 560, and D it's 1K given in ohms. Okay, so friend, this is the question given and they're asking for the RS. Find out the value of RS. So this is the JFET they have given, JFET. And for the JFET, what is the current equation? ID equal to IDSS 1 minus VGS by VP whole square. Is it? So IDSS is given, ID is given. Let's put the value. IDSS 6.4, milli and milli will get cancelled. This is 10. 1 minus VGS I have to calculate, G and S, VGS. This one is very important, VGS, to calculate this RS. And VP is given minus 5, so this will become plus 5 and whole square. Is it okay? So this will be 64 divided by 10, 100, 1 plus VGS divided by 5 and take the root. So it will be 8 by 10, so 0.8. So 0.8 equal to 1 plus VGS divided by 5. Okay, so it will come over here. So it will be 0.2 and minus 1. VGS equal to minus 1 volt. Now you have find out the VGS equal to minus 1 volt. Let me erase some part, then I'll show you. VGS you have found minus 1 volt. Now you will apply the KVL in the input mesh and you will get the value of RS. They're asking for the RS only. And remember one thing, for JFET or MOSFET, the input current, that is IG, is always 0. Okay, it means ID is equal to always IS. Okay, so VGS you calculated minus 1 volt. Now we'll apply over here. In this circuit, the current is ID only, because IG is 0, so ID is current to the I source current. So I'm going to apply here 1 volt, and this is minus RSID equal to 0. Is it okay? So RSID is 1 volt. What is ID? RS is 1 by ID. ID is this 6.4 milli. Okay, so RS will be 6.4. Okay, so when you will divide, it will be nearly 150 ohm. Option A is correct. Let's take another problem, and the problem is again gate problem, and the given in the question is an n-type JFET has IDS is given. IDS is given 1 milliampere, and VP is given minus 5 volt. Its maximum transconductance is GMO. They are asking. This is GM max. You know it. And GMO's formula we have seen, minus 2 IDSS divided by VP, if you remember. Minus 2 ID is 1 milliampere divided by VP is minus 5. So this will cancel out. We'll be having 2 milliampere divided by 5. So your GMO is, you don't have an option for this, 2 by 5. And milli, this is not milliampere now. So this is mho. Okay. It will be Siemens. Okay. So it will be 0.4 millisiemens. This is your GMO. This is the maximum. Okay, friends. Now this is the GATE 2003 problem and 2 marks problem. And the problem is the action of JFET. Talking about JFET, action of JFET, equivalent circuit can best be represented as, means JFET equivalent to, 4 options are given. Current control current source, current control current source. Option B is given. Current control voltage source, current control voltage source. Option C is given. Voltage control voltage source, and the last option is given, voltage control current source. Do you remember it? Current control current source is BJT, and FET is voltage control current source. At the output we are getting current only. So this is FET. Is it okay? So for the FET, the input is infinity. If input is infinity, means it's a very good system. We can control it very easily. This is also 0. Infinity. But for the BJT I'm talking about, for BJT Rin is very low, but R out is very high. Okay. So this is 2 marks question directly. Okay. So we'll meet in the next class, friends, with some more numericals and problems based on JFET and MOSFET. So the concept will clear to you people. Okay.